Okay, in this video, we're going to take a look at Taylor polynomials. So earlier in this course, we took a look at how we can approximate a function near a point using linearization. And I'll just remind you of the formula to approximate the nearby value. You take the y value and you look at the slope near that point and the change in the x value, and you can approximate a point near a point you're interested in. And this is called a first order approximation. Since the a value into L of x and the a value into f of a would be the same, and same with the derivative of those. They would have the same value. And this can continue. So we continue this pattern past the first derivative, and we look at, well, does f double prime of a equal g double prime of a? If this sort of thing continues all the way up to the nth, so the nth derivative at a is equal to the nth derivative at g, then what we say is these two functions agree with each other. They have such similar characteristics that they agree to order n at x. That t sub n of x, this Taylor polynomial, nth degree, is equal to f of a plus f prime of a over 1 factorial times x minus a. That's the linearization. And then we can add on a second degree over 2 factorial. That's a squared. And we just keep adding the derivative over n factorial times x minus n. So we've seen the basic functions. Let me just create some more room. Of t sub 0, well, t sub 0 of x just means that it's just f of a, it's just the y value. A point approaches itself or approximates itself. If we increase this to the first Taylor polynomial, then we get linearization, and so this gives f of a, it gives you a line that mimics what the function looks like. And now we can add more. So we can add a second Taylor polynomial. And we can add a third degree Taylor polynomial, in which we really just add a third derivative term to the end. And this is 3 factorial, so this is over 6 to the end of this, this expression. And we can also rewrite this using sigma notation, so it can look like this, so that we can just see that we're constantly adding up these terms. And when a is 0, when you center this function at the origin, this has a special name that t of n now becomes named the nth Maclaurin polynomial. Okay, so let's try finding some of these polynomials. I'll give you an example here. So we're going to find the fourth degree Taylor polynomial centered at a equals 3 for the function root x plus 1. And the first thing we need to do is evaluate all the derivatives up to degree 4 with an a value of 3. So I'll do that for you. And we have to evaluate each of these at 3. So let me do that for you as well. In which case we get 2 and 1/4 and negative 1 over 32, 3. And so these are necessary just so that we can plug them in to the expansion fairly quickly. Remembering that this T4 will have the form f plus, let me write it out quick. And now since we have those f prime of 3's, we can substitute them in fairly quickly. I'll just create some space. And so I get this constant term of 2, and then I get 1/4 times x minus a. I get 1/2 of -1/32. And of course, this isn't x minus a, this is x minus 3. And so x minus 3 gets squared. I'll continue on the next line here. And then I get 3/256 times 1/6 x minus 3 cubed. And for my final term, I get -15/2048 times 1/24 times x minus 3 to the power of 4. You can simplify some of these terms, and this will create a degree 4 polynomial for you that mimics what is happening near a equals 3 for our original function. And what this looks like visually is I have a function that is a square root function that is moved 1 to the left as my original function. I'm looking at this a value of 3, and I'm saying, can I design a polynomial function that mimics this near this point really well? And it turns out that there's a degree 4 equation that mimics this extremely well near that point. In fact, if I were to grab a graphing calculator, this would cruise along like this and do a really good job here. And then, of course, they're going to diverge. So the square root function is going to continue, and my degree 4 equation is going to go back down, kind of like a downward facing parabola, but it's degree 4. And I'm mimicking the square root graph near this point as best I can with this degree 4 polynomial. Let's try another one. We'll try a Maclaurin series, or a Maclaurin polynomial, just so you can see how it's similar and different. So let's take a look at this question. Let's see if we can find the Maclaurin polynomial for f of x equals cos x. Or find the polynomials for this, and then show that the estimate gets better and better over larger intervals. So let's just draw a sketch of f of x equals cos x. And it turns out that if we were to take the first Taylor polynomial, that we would, let's actually do the first Taylor polynomial like this, that we would get a value of 1. And so this linear function here, remember Maclaurin polynomials are centered at a equals 0. So this Taylor Maclaurin polynomial here approximates the cosine wave quite nicely at 0, but not very well at many other places. If I upgrade this to the Taylor polynomial at 2, it turns out that that's also the same as the Taylor polynomial at 3. You get this calculation, 1/2x squared. So this is a bit of a better approximation. If I just redraw this cosine wave, it now is this downward facing parabola. And so it's a little bit better. It covers a slightly larger region. If I take that cosine wave and I go look at the next ones, which are T4 and T5, it turns out that these ones become that one, and then I add some more Taylor polynomial to this, and it becomes a degree 4 equation. And now it starts to look, this is just an estimate, look even better. And of course, the Taylor polynomial, Maclaurin polynomial for T6, T7 is even better. Just give you a quick little sketch of what that one looks like. There's your cosine graph. So this actually, kind of does a larger and larger zone where it is matching up nicely.